well. Okay, so do you want to talk about lab? Kidding. Everyone's like, no? Homework questions, I'm guessing? I'm going to open another window. I think it's going to get warm in here. There's more space up front if people want to move in a bit more. 1, 2, 3, 4. I was going to say, what questions do you want to do? I don't know. These are pretty long questions, so we'll see how it goes. Does anyone have specific questions about any of these things? Yeah.
Just like 3A, I'm kind of confused as to like how to determine like the best anion.
3A. So let's go ahead. Let's start with problem 3. Actually, does anyone have the homework? Can you read what the homework says? Somebody, anybody, bring. Oh, we gotta let Deminda in here as well to get his stuff. Yeah. Question 3. Yeah, go for it.
In a 2-liter solution with an initial mixture of 0.45 molar silver ion and 0.16 molar calcium ion, and for first part.
Yeah.
So which anion would be best for separating the two compounds between carbonate, iodate, and phosphate? Explain your answer and state which will precipitate.
Carbonate, iodate, and what was the other one? Phosphate? Yeah. From 2 to 4. Wait, what time is it? Noon to 2. Noon to 2. Yeah. So, it's nice and neat. So, 3A. How do we pick which anion we're going to use? There's some space right up here if you want to sit under the camera. Yeah, so all we're going to do is we're going to look at the KSP values. Now, on the homework, I assume that you have access to the textbook and the internet and all kinds of other sources, so you can look up KSP values. I'm just going to pull out the old textbook and look at the KSP values, and we can essentially make a table to try and figure out what is best. So we're going to look at these 3 things. We're just going to compare KSP values. We're going to look at the silver. We're going to just make a little table, and we're going to look at the calcium. And hopefully, we can find all the KSP values for this. Oh man, I don't think we can fit more people in here. I mean, I guess we could. Like, maybe we could. It's more people than I was expecting. In any case, let's keep working on this. So, if you've got internet handy in your phone or something like that, look up some KSP values. I'm going to flip through this textbook and find them as well. I'll look up the silver KSPs if somebody else, all of you. Oh, great. We've got them all written down. So, silver carbonate, 8.4 times 10 to the minus 12. Silver iodate, 3.17 times 10 to the minus 8. Silver phosphate, 8.89 times 10 to the minus 17. And where did you get those?
Oh, I just have like a piece of paper with all them printed.
Okay. So it's the there's one of the links I gave, I think, is a PDF that's printable. Right now, this gives us no information about which anion would be best, right? We want to find the largest difference in KSP. So let's go ahead and look at the carbonates. 3.36 times 10 to the minus 9. 6.47 times 10 to the minus 6. And 2.07 times 10 to the minus 33. Wow. Okay, so when we start to look at this, we have to think, okay, so what is going to be the best separation? Let's get backpacks tucked underneath things more and try to get a few more people in here. So when we're looking at this, we're really just going to be looking at orders of magnitude, right? So we can do 10 to the minus 12, 10 to the minus 9. That's 3 orders of magnitude. That's about 1,000 times different. There's space here and here if people want to come in a bit more. Just get cozy. 10 to the minus 8, 10 to the minus 6, that's 2 orders of magnitude.
Can you like compare the KSPs if they're not like a 1-to-1?
Ah, good question. So The question is, can we even directly compare these when we've got a +2 and a plus? So when we think about this, the AgCO3 would be an Ag2CO3, and we know that's going to give us something like KSP equals 4x cubed, whereas the CaCO3 is going to give us something like a KSP equals x squared. Make sure that's all visible on there. Yep, great. So in this case, normally if we wanted to say which one was more soluble, it's hard to tell which one's more soluble in this case. But since I'm comparing these two, I'm always going to do cube root of this one, square root of this one. So I'm doing the same mathematical operation to this, and this, and this, and these three, right? So eventually I'll get, comparing the KSPs directly is not perfect, but it's going to give us a pretty good idea since I'm going to be doing the same mathematical operations in all three comparisons. If I wanted to compare across, if I wanted to compare silver carbonate to calcium iodate, I would have problems with that. But since I'm doing a comparison just between those, we can kind of do it and it should work. But it's not going to tell us which is more soluble. It's just going to tell us which has the biggest difference, right? So this one looks best, right? The phosphate. So when we look at the phosphate, we've got 10 to the minus 33, 10 to the minus 17. That is going to be a lot of orders of magnitude. 16 orders of magnitude. So, you know, this one's off by like 1,000, this one's off by 100, this one's off by a couple million. Like a million millions. It's got a lot of zeros. So that one looks the best, but if I remember correctly, something weird happens when we pick that one. I just want to make sure we've got the right number as well. I've got a slightly different number out of this textbook, but still the point is big difference. So based purely on the KSP values, it looks like phosphate is going to give us the biggest separation between the two. Now, the reason that this gets a little bit tricky, if I remember correctly, it takes a very small amount of phosphate to saturate this solution, and so that's going to have some problem with it, but it looks like phosphate's going to be best. Based off of what we've learned in this class, we say, okay, which anion is best is going to be the one with the biggest separation between the KSPs, phosphate. Should we see how it goes? So also in this case, I think I'm about to answer question part B. So this is looking at problem 3. Part B asks, someone else who's got the homework handy, what's part B ask?
Your answer in part A, what concentration of anion would provide the best separation?
Oh, okay. I thought it was going to ask something else. Here's the question I thought it was going to ask. I don't remember the homework perfectly. I was going to ask, which one is going to precipitate? Thumbs up for silver, thumbs down for calcium. Calcium, right? It's got the smaller KSP value. That means it's more likely to stay a solid. Then when we get to question B, it's PO4, 3 minus to saturate. And what's it exactly say? Saturate the
biggest separation. That's what they want.
Oh, what amount is necessary to saturate? Or wait, sorry, read the question.
It says, what is the concentration of anion? What concentration of anion would provide the best separation?
Okay. I see why I asked the question that way. So asking the question that way, I don't kind of give you a clue to what you're supposed to do, but I already accidentally wrote the clue, then I erased it. So what are we supposed to do in this problem? Yeah?
Saturate the most soluble compound.
Saturate the most soluble. So if you remember, this is a separation by precipitation or competitive solubility. We always follow the same 0 step that we don't really care about. 1 step is saturate. Saturate the most soluble. I don't know how legible that is on the screen. green doesn't come across well and I'm writing small. Saturate the most soluble, and step 2 is what I call redissolve. So I call it redissolve the precipitate. So essentially what's happening here is our stoichiometry calculation, which we're kind of skipping, overestimates how much solid we form, right? So if we wanted to get the right value, naturally this would be something that kind of asymptotically, as the two things mix, it naturally kind of like just approaches the right level. But that's really hard to calculate. So what we're going to do is we're going to look at how does it we're going to split it into 2 steps and essentially overestimate and then correct. And we've been doing that with every calculation where we've done precipitation and insolubility. The only catch here is first we're going to figure out the maximum amount of phosphate we can put in. We're going to saturate the one that is most soluble. Man, that's a lot of people. Okay, so how do we set up the saturation problem? Right, we're going to look at the solid, and right now we don't have any solid, right? And we want to get to the point where we don't have any solid. So we're going to take our silver concentration, 0.45 molarity, and we're going to find the phosphate concentration that would be at equilibrium, that point where we're not going to form any solid. So we're just going to find some value x there. And essentially, I'm skipping most of the ice table and just doing the equilibrium part. Because this isn't actually, and I should explain, saturation describes a state, not a process. So saturation happens when you add ions together and get to the maximum, or when you have a solid dissolve and you get to the maximum. Question?
Is it PO4 3 minus?
Yeah, it's totally. Oh, it totally is. You are correct. I've been doing that this whole time. Oh no, I didn't. This is the first time I made that mistake. Oh, you know where I made that mistake earlier when I said it would give a KSP of like 4x squared or 4x cubed? It would actually be 27x to the 4th. So I did make a mistake earlier. So yeah, this would go like this. Is oddly enough not going to affect this calculation. Because I'm still going to have approximately 0.4, I'm still going to have the same molarity here, right? I'm not changing this. So even though I made that mistake, this is one of those odd situations where that mistake doesn't affect the calculation. I'm looking around the room trying to figure out how we can get more people in here. I don't know how. I don't know how. Can you all see okay? Kinda. If someone's comfortable sitting on the desk over here, they can do that, and then like yeah, there's a little space in here. Just come in, make yourselves comfortable, make friends. So can you all solve this? We're just gonna have the KSP 8.89 times 10 to the minus 17 is equal to 0.45. Oh, you know how I said it wouldn't change the calculation? I was wrong, because that 0.45 needs to be cubed. If I had the wrong chemical formula and if I had the wrong chemical equation, I would make the mistake because I would square that instead of cube it. That would make the answer wrong. We then solve for x, and if you've got a calculator, help me out, please.
1.975.
No, the 27 is not going to come into account because we would if we had like a plus 3x here, but since we can essentially use the x as small approximation because that's so small, that's not going to come into account. So if I looked at just the KSP expression, I'm going to have KSP equals AG cubed, AG plus cubed, times PO4 3 minus. My AG concentration is just 0.45. There's no 3 in that case. and my PO43 minus concentration is just the X. I can't do that division in my head.
It's 9.76 times 10 to the negative 6.
Cool, that's X. And of course, like I mentioned in class on Monday, anytime we calculate an X, we have to slow down and say, okay, what I just calculate, what does the number represent, and what does that chemically mean? So we look at this and we say, okay, its chemical meaning is pretty straightforward. It's my phosphate concentration. So I should put units of molarity on here. And I should put molarity, and I can even put the fact that it's PO43 minus. And what does that molarity, what does that concentration mean? Yeah.
I think it's to the negative 16.
Is it negative 16?
Yeah.
Well,
The concentration of phosphate is wrong.
negative 16?
Oh yeah, sorry. Did I know?
You might have said 16. I might have just written down 6.
No, I definitely.
Okay, negative 16. That makes more sense. Because we're dividing by something that's like 0.1. Even if you cube it, that's still going to be 4, 16, 50 something, which is going to be 0.05 something. You're going to divide by 0.05. You should get something that's still in the order of negative 16. Something I always encourage, I haven't encouraged it as much in this class as I have in my 124 class. It's always a good idea to think about what ballpark your answer should be in before you touch your calculator. So that way you don't do something like get 10 to the minus 6 instead of minus 16. Because now that I'm looking at the math, I'm like, oh yeah, of course that should be minus 16. But when someone just shouted it out without me thinking, I was like, minus 6 sounds fine. I trust calculators. But you're using the calculator, so double check. That's the number, that's the concentration. What does that concentration mean, though? What does that represent in terms of what's happening here? Tell the person sitting next to you. This is almost like a mini lecture. Oh,
Extra space that you have to wiggle around.
So, hopefully the person sitting next to you said something along the lines, or you at home thought this, thought something along the lines of, that is the maximum concentration of phosphate we can put in solution, right? So this is the amount of phosphate we can put in that gets us just to this point where we have not precipitated any of the silver. So we've already done step 0, all the calcium has been precipitated. We want to add as much extra phosphate as possible, and there's a limit to how much extra phosphate we can add. Ideally, we'd add just tons, but because the silver's there and we want to keep the silver in solution so we can collect it and make money off of it. Something like that, like, you know, like silver mining. This is the amount of phosphate we could put in solution that gets us right to the point before we make any precipitate. If that's our X value, our reaction will stay as ions. If we put just 1 drop more, we'll start to precipitate and we'll lose some of our silver. What's part C ask us? Any questions on that? Yeah.
Yeah, if you put in less, then would the silver still stay as like
Yeah, so you could put in less. However, that's going to affect step C, and we'll be able to tell why we want why we want this concentration to be as big as possible when we're looking at what I called step 2 in the process, or part C of the problem. Short answer is the common ion effect decreases solubility with increased initial concentration. So if we want to decrease the solubility of calcium, we want the largest concentration of phosphate possible. And I think that's what part C of the problem asks.
It says, what is the concentration of each cation at the maximum separation? And you use the hexadecimal approximation higher.
So concentration of each cation. So if we did this correctly, we already have the concentration of silver. Right? Silver's concentration should not change at all if we did this correctly. So the concentration of silver is already known. 0.45 molarity. The concentration of the calcium is the interesting thing. Because we precipitated all of the calcium in step 1 or in step 0, none of that calcium is there now. So then we have to say, okay, we know that 0, having 0 concentration isn't real. So I have to look at how much of this calcium phosphate, this solid we produced, is going to redissolve. Wow, this is tricky. So Ca2PO4, wait, Ca3PO42. That'll be interesting. So we know that this is going to fall apart to 3 calcium 2 pluses plus 2 PO4 3 minuses. I know that's right because that gives me a charge of 6. Charge of 6, that's neutral. Neutral, we're good. So we're going to set this up as an ice table, just like we always do. We don't care about the solid. Our calcium concentration at the initial of this point should be nothing because in step 0 we precipitate all of the calcium, we have nothing left. Our phosphate concentration is based off of the previous answer. And we can just plug that in here. 9.76 times 10 to the minus 16. And I think this is the part that makes the phosphate a weird answer, is having such a small value for the phosphate concentration makes it so the x is small approximation doesn't work that well. But let's see if that's true or not. We're going to have our plus 3x, and this is where it is going to be, there's going to be a factor of 27, because that 3x is not negligible. We're going to have a plus 2x, we're going to have 3x. I'm still going to use the x as small approximation because I don't feel like solving a quadratic. So I'm going to say this is approximately 9.76 times 10 to the minus 16, and we'll see if that gets me in trouble. So I'm going to bring this work up to the top here, just because I need more space.
So in part B, for your KSP, that was the KSP of the silver phosphate?
That was the KSP of the silver phosphate because we were saturating the silver.
But, okay, but shouldn't your KSP be something else? It shouldn't be 2.6 times the negative 18 or something like that.
Wait, which KSP?
For the silver phosphate.
8.89 times 10. What number did you get?
I got 2.6 times 10 to the negative 18.
Close enough.
Oh, okay.
When you get down to these low KSP values, you'll see quite a bit of variation between different texts.
Okay.
As long as you did the same process and you got the same kind of idea, you'll be fine. I will provide the KSPs on the exams and the quizzes, so I'll give you a KSP, so that kind of uncertainty is removed. But when you're comparing answers with your fellow classmates, you might have that problem of like, oh, we use different KSP values, and just be aware if your answers are slightly different, that might be why. So I'm going to take this calculation, bring it up here. We're going to have 2.07 times 10 to the minus 33 is equal to 3x cubed times 9.76 times 10 to the minus 16 squared. And I think x is small is going to fail. I think it's going to fail pretty terribly. Yeah.
Why doesn't it work if, like, to the negative 16 is really different from to the negative 33?
Well, so the problem is, and remember, that's what we've been using as like a rule of thumb, is like we can compare the concentration to the KSP. but really what we want to check is what is the x value after we do the calculation. So based on the difference of the -16, -33, I'd say, yeah, I think this is going to work. It's going to be -16 squared, which is going to be on the order of -30. So I really want to check the x afterwards to tell. But based off of that, I'm like, I think it'll work. But when we actually solve for x, I think it's going to fail pretty bad.
So when it fails, we're gonna have to do it in quadratic.
Yeah.
It's 0.043 or 0.0432.
Is x small? No, x is not small in this case. So in this case, the x is small approximation completely fails. And that's because our concentration of our phosphate is so incredibly small. This is like x is not small at all. So x is small approximation fails. We could theoretically say, okay, we've got some numerical value, but it's wrong. It's wrong. We would actually need to solve, and it's not even going to be a quadratic equation or a cubic equation. This is going to be an x to the 5th equation, because we're going to have 3x squared, and then we're going to have a plus 2x, 3x cubed plus a 2x squared. We're going to have an x to the 5th equation to solve here. Things that make it so this doesn't go as wrong is, if I remember correctly, if you used the textbook values that I have, which are not these numbers, the x is small approximation doesn't fail as bad. You still get like a 20% error, but you get like a reasonable answer for your concentration even though you have a 20% error. So it's not great, but it still is a little bit better. This is just complete failure of the x is small approximation.
What would be reasonable?
We would need something on the order of 9 to the -17. 9 times 10 to the -17 is what we would have to get something that's reasonable, right? Something that is at least 10% smaller than this in order for x to work. So in this situation, we've done all of the calculation correctly. We've got the right concept. And the thing that becomes important to me, and I would say, if we did this on a quiz or a test, I would say, use the x is small approximation, get an answer, and tell me if x is small is good or bad. And you would get this, and you'd say, okay, this is the answer if I use the x is small approximation, and it's very obviously very bad. I would not do the extra step of then saying, okay, now solve the 5th root equation problem. I wouldn't do that to you. Something I might do, I wouldn't do it on the quiz, but I might do this on an exam. I might put like the actual concentration, if you did the solution, is this value, what's your percent error? Right, and in this case, your percent error would be like 1,000,000%, but hopefully your percent error would be smaller than that. Question?
So determining that x is small approximation doesn't work, should we look at the actual x value or should we look at the concentration?
You should look at the x value compared to the initial concentration. And the reason I do it this way is because depending on if you're looking in the textbook or if you're reading, if you've seen this in another class, there's this trick that I don't like. I do like it, but you do concentration over KSP is, I always forget if it's greater than or less than because I never use it. But let's go with less than 400. I think it's greater than 400. Because I want concentration to be bigger. Yes, greater than 400. There's something like this that works. This only works for the 1-to-1 ratio system though. Because this you can mathematically prove through 5% error of concentration. It only works for the 1-to-1 ratio. If we wanted to do this 3-to-2 ratio, this rule of thumb doesn't work. So I always compare my x value to say whether, to my initial concentration to say whether it worked or not. That's how we do problem 3.
would one of the other anions work better? Like carbonate had like a difference in magnitude of like 1,000.
Did I ask that in that problem, or is that problem 4?
I think it's 4.
Let's try one of the other ones and see what happens. It is 3?
Yeah.
So I think in problem 3 I said, what if we used some different anion? Right, because one of the problems we have here is this small concentration, the X is small approximation failing. One of the other anions, even though it would give, like, if we actually solve this would probably give us better separation, right? Our concentration of calcium is going to be on the order of -16, whereas our concentration of gold is still going to be at like 0.45. But let's go ahead, let's redo this. I think this will also be nice to see another calculation. And let's see what happens if we do something where the X is small approximation actually works. Should we try, is it carbonate or iodate? Which one do you want to do? We can do either. And notice we can actually do separation of ions for any of the counter ions, in this case the anions we want to use. We can do separation for all of them. It's just a matter of which one is going to do the best separation. So we're going to continue with problem 3, but we're going to look at it another anion. Finger number 1 if you want to do carbonate, finger number 2 if you want to do iodate. Everyone wants to do carbonate. Question? Was there a question there as well? No, okay, so we're going to do carbonate. Someone do me a favor. What is the... Oh, I didn't put that wrong before. I did it for carbonate instead of phosphate, so it was 4x cubed. But what is the KSP for silver carbonate? I need a couple people to tell me the numbers they got because we're going to have a couple different numbers.
8.1 times 10 to the negative 12.
Yeah.
Okay, never mind. We all got one value. Great, that's better. And for calcium carbonate.
3.3 times, or 3.3 times 10 to the negative 9.
Yeah, that's what I got.
Okay, so we've got a couple strange things going on here that's going to make this problem different than the last problem. First off, we've got different KSP values. Our KSP values are closer together. But also notice I'm going to have something that's like x squared, and I'm going to have something that's like 4x cubed, instead of having x to the 4th, x to the 5th, which we had in the last problem. So, you know, taking 4th roots and 5th roots is going to be more complicated. It's also going to have a bigger change. So even though we had a separation of 17 to 33, which is, I have to do that in my head again, a separation of 16, we're going to be taking the 5th root of that separation. Here we've got a separation of 3, and we're going to be taking like a square root of that separation. So even though I think the other case, the phosphate, would give us a better separation, I don't think it would be that much better because we're dealing with 5th roots instead of square roots. But let's see that for real and see how it goes. First thing we do, which thing's going to precipitate first? So notice in this case, this is another change. This is another change, right? So in that previous problem, or in the same problem, but with the other anion, with the other counter ion, calcium precipitated first. With this change, we're also changing what precipitates first. So now we're going to be precipitating the silver first, which means and that's going to be in step 0, which means in step 1, what do we do? Saturate calcium. It's the calcium in this case is going to be the most soluble, so we're going to saturate calcium.
We're going to silver will precipitate because it's smaller KSP value.
Exactly. Right. So sorry, I'm wondering if that's true because now remember how earlier I said it didn't matter that they were different? Now that we're directly comparing them and asking which one is more soluble, now the fact that they're different does matter. Right? So let's go ahead and do a check of which one's more soluble in water. I'm just curious. I'm very curious. I think it's still going to be silver precipitates first, but I just want to double check. So how do we check that? Which one's going to precipitate? Which one's more soluble? We actually can't directly compare the KSPs in this case, because we're going to be taking a third root and a square root. Yeah.
Where did you get those from the 4x cubed?
Oh, so where did I get the 4x cubed? Let's go ahead and do this. This is going to be kind of like which precipitates first? I can't write the word first for some reason. Which precipitates first? So we're going to essentially compare these. We can do calcium carbonate first. Calcium carbonate, solid, is going to fall apart into calcium 2 plus CO3 2 minus. If I'm doing this in water, well, that's an X. I'm just going too fast. Plus X. You notice I'm essentially just skipping the ice table, right? I'm going to get KSP equals X squared. This is going to give me an X value of
5.74 times 10 to the negative 5.
Is that 5.74? 10 to the minus 5?
Yes.
I'm going to do the same thing for silver carbonate, where I could do the whole table again. But again, hopefully we're getting good at these and we can kind of start skipping these. I'm going to get KSP equals 4x cubed. I'm going to get x is equal to
1.26 times 10 to the negative 4.
Ooh. Look at that. We have to be careful about which one we think is going to precipitate first. Because of the way that we have the cube root versus the square root, that's going to throw it off. So it turns out my gut reaction of saying, oh, the smaller one precipitates first, not correct. Because of the number of ions that are going into solution. So when I just jumped and said silver precipitates first, my gut reaction was actually wrong. Calcium is going to precipitate first. It is going to be the one that is less soluble, because we end up with less ions of it in solution. Also notice these numbers are pretty close to each other, which means we're not going to get a great separation with this, which isn't surprising because, again, just comparing the KSP values, we're only like 3 orders of magnitude. When we look at the solubilities, the molar solubilities, we're only 1 order of magnitude off. This is not going to give us a good separation, but it'll still give us some separation. Question?
On the last one, we didn't have to do that because it was such a big difference on the orders.
On the last one, we didn't do that, and I think it's okay because it was such a big difference on the orders.
But technically, we should do that.
Technically, we should have. But minus 33 with the 5th root versus minus 16 with the 3rd root, minus 33 should still win. But these, since they were pretty close, I couldn't just eyeball it like that. So now that calcium is precipitating first, we are going to saturate silver. So this is actually going to be quite familiar to the last problem. So step 1, and this is the thing that clued me in that I might have made a mistake, is this idea that saturating the one that's more soluble. It's not saturating the one with the smaller KSP, it's saturating the one that's more soluble. So I have to find the molar solubility to compare that. So let's go ahead and saturate the one that's more soluble, the same way we did it last time. We're going to have Ag CO3, sorry, Ag2CO3, going to 2 Ag plus CO3 2 minus, instead of an ice table. And again, because this is the saturation step, I'm not really looking at this kind of like an initial thing where solid is dissolving. I'm adding extra carbonate. You'll notice the equilibrium step, the thing that I care about, still comes out the same way, whether you treat it this way or not. The only reason, sorry, that's not 0. This is still 0.45. This is 0. This is plus 2x plus x. The reason I don't like doing these steps when we're saturating is because we're not saturating because solid is falling apart. There's no silver carbonate solid. We're saturating by adding ions into solution. So I don't actually like doing this change step. I like just doing the equilibrium where I say 0.45 and then I'm adding the right amount of that x in order to get the saturation point. Because remember, saturation is a state. It's where we are, not how we get there. We can get saturation by adding ions or by dissolving solid. In most of the problems we've solved up till now, we've gotten to saturation by dissolving solid. But this saturation in the competitive solubility, this saturation is made by adding ions. So I don't really like doing this change equilibrium step, even though it comes out the same. It just feels like it's misleading to me. So we go ahead and we say we're going to have KSP is equal to 0.45 squared times x. I can actually just plug in the KSP value. 8.1 times 10 to the minus 12. I'm going to get an x value of
4 times 10 to the negative 11.
Okay. I'm worried x is small is going to fail again. Let's see what happens. So then we're going to go ahead and we're going to say,
Carbonate, right?
what's that? Oh, yes, sorry. That's the concentration of carbonate, my x value. Remember, even I should do it, right? After I solve for an x, I should stop and say, okay, what did I just solve for? I did not solve for silver concentration. Silver concentration is going to stay the same because we're not adding any silver. There's no solid that's actually dissolving, and we're not adding any silver. Carbonate changes. It's not because the solid's falling apart. It's because we are adding carbonate to solution. And we're going to add until we get this very small concentration. This is like atmospheric carbon dioxide dissolving into water would create this level of carbonate concentration. This is a really low concentration. So then we're going to go ahead and we're going to do step 2. Redissolved precipitate. Again, our stoichiometry that we skipped is going to overestimate how much solid we form. And now some solid's going to redissolve based on this excess carbonate being in solution. So we're going to look at CaCO3 going to Ca2 plus CO3 2 minus. Oh yeah, x is small is totally going to fail. Totally going to fail again. We're going to have a 0. We're going to have 4 times 10 to the minus 11 plus x. If we do use the x is small approximation, and what I would do on a quiz or a test is I would say use the x is small approximation and say if it's good or bad. We would say this is 4 times 10 to the minus 11. And then we would say KSP 3.3 times 10 to the minus 9 is equal to 4 times 10 to the minus 11 times x. How can I tell it's going to fail? 3.3 times 10 to the minus 9 divided by 10 to the minus 11 is going to be like 100. That is not small. The x is small approximation fails in this case again. Somebody actually calculate the x for me so we can see how poorly it fails. Yeah?
So on the quiz, if x is small fails, you just write in this is
Yeah, so I would ask you, I'd say, what is your answer with the x's small approximation? And then I would say, was that good or bad?
82.5.
And I would not ask you to solve the quadratic. I kind of want to solve the quadratic just to see what the answer is right now, even though I'd never ask you to do that. And this one doesn't even seem like that bad of a quadratic, so I'm going to do it. What time is it? I don't want to waste our time, but I'm also really curious. I just want to make sure, is everything still working? Yeah, everything's still working. Okay, so. Oh, I erased everything I wanted. So, 3.3 times 10 to the minus 9 is equal to 4 times 10 to the minus 11 plus x times x. So I would have 0 is equal to x squared plus 4 times 10 to the minus 11x minus 3.3 times 10 to the minus 9. And we would solve.
Oh god, so scary.
Okay. They can still see everything. The problem with solving is, so I've solved some of these in like the online calculators, and they solve them wrong. Most of the online calculators see the numbers they get out of this and just say it's 0. They just say your answer is 0 because it's approximately true. They get something that's on the order of 10 to the minus 12, 10 to the minus 16, and they just go, yeah, let's call that 0. So we would actually have to do this the old-fashioned way. Negative 4 times 10 to the minus 11 plus or minus square root b squared minus 4 times 3.3 times 10 to the minus 9. What's that? B squared minus, oh yeah, so this would be a positive overall, all over 2. We would actually solve that. So you're going to get something, that's not that hard to solve actually. Now that I'm looking at it, after you write it out with the whole x equals negative b plus or minus square root b squared minus 4ac all over 2a. Because 4 times 10, because we're going to use some small approximations here, right? This is going to be like 12 times 10 to the minus 9 plus 4 times 10 to the minus 12. That's just going to be 4 times 10 to the minus 9. You're going to take the square root of 4 times 10 to the minus 9, and you're going to get something that's like 2 times 10 to the minus 4. You're going to get something that's like 1 times 10 to the minus 4. And when we solve it that way, when we actually do all of the math, we're not doing an approximation. So even though you get something that's much larger, your answer is your answer, right? So when we did this with the approximation, when we did it with the bad approximation, we got 89. And we know that was like total nonsense. That's silliness. But when we actually solve the quadratic and we get a value of
5.74 times 10 to the negative 5.
that, even though it's still much bigger than 4 times 10 to the minus 11, that is the actual answer. No approximation. That's just it. So that's the actual answer. This is going to be the concentration of calcium ions left in solution, whereas our concentration of silver ions left in solution is 0.45 molarity. Notice that this is a reasonable concentration for separation, actually. Right? We went from a concentration, I can't even remember what the concentration of calcium was. We went from a concentration of, what was it, like 1.7? 0.16. We went from a concentration of 0.16 down to a concentration of 5.74 times 10 to the minus 5. That's a pretty good drop. Instead of having things that were a factor of 4 different from each other, we now have two concentrations. This concentration, this concentration. We have concentrations that are a factor of 10,000, or sorry, a factor of 10,000 different from each other. So that's a fantastic separation. We went from a factor of 4 separation to a factor of 10,000 separation. But I would never actually ask you to solve the quadratic like this. I was just curious. I wanted to see what it did. I don't want to do problem 4 because it's just doing this again. So let's look. Number one or number 2? Both. They're the same thing. Okay, show of fingers, 1 or 2. Oh, jeez, that is such a close split. How about we do half of each? That sounds worse, huh? 2 has more parts, but it's all the same parts. I just split it up into more steps for some reason.
So, which one did we decide on?
They're still debating.
I see.
Do me a favor. 1s and 2s again. If you're a 1 or a 2, talk to the person next to you, convince them to change, because I need a majority. It's too closely split. They're really the same thing. How about that? How about we do number 1 and set up number 2? Did anyone change their votes?
Alright, let's do 1.
Oh, a couple people changed to 1 out here. Okay, we'll do. How about we set up number 1 and then do number 2? So, here's what we're going to do. We're going to read the 2 problems and see if they're any different at all. What's problem 1?
Consider the formation of solid barium iodate from the mixing of 7.5 milligrams of barium chloride being dissolved into 500 ml of 0.023 molar sodium iodate.
Oops, that's not a 3, that's an M. Okay, so we're going to look at the formation of barium iodate by mixing these 2 things together. So this is a mix precipitate forms. We're going to overestimate the amount of precipitate forms and then correct with our equilibrium and then say, was that correction necessary or not? Problem 2. So someone who wants to do problem 2, read out problem 2.
Consider a solution that is made from mixing 35 milliliters of 0.22 molarity of AgNO3 and 82 milliliters of 0.22 of Na2SO4.
So in this case, what's going to happen is you're going to do a reaction. You're going to form silver sulfate. Mix precipitate forms. You're going to look at how much redissolves. And you're going to say, was that redissolve significant or not? I think the only thing that's extra between the 2 is number 2 actually asks you to calculate the net amount. So it actually asks you how much total solid did you form. Whereas in this one, it turns out that the correction is kind of small. So this one actually is a little bit more tricky. Knowing that number 2 is tricky, are you number 1's going to switch? No. Let's set up. So if we set up number 1, it's going to be, well, I mean, both these, we've done these so many. Okay, so number 1, what we're going to do is first we're going to say barium chloride plus sodium iodate forms barium iodate plus spectator. I don't care about the sodium chloride that's formed. I don't care about the salt. We need, this is technically, so here's one of the things I'm going to do that's a little bit weird. I give you a solid amount, but I'm calling it aqueous here. Right? One of the weird things that we keep doing is we're picking where we take this snapshot of this reaction, right? We're freezing time. So essentially what I'm doing by freezing time here is I'm saying, look, the barium chloride goes into the 500 milliliters and it's going to dissolve. But I want to take a snapshot after after it dissolved before it reacts so I can consider the stoichiometry of what's going to happen. So putting aqueous here is just recognizing the fact that once it hits the liquid, it will dissolve. And in nature, it's actually dissolving and reacting at the same time. But to kind of separate out those two steps, we're going to say it dissolves and then it reacts. It's not how nature happens, but it makes the calculation a lot easier. So we're going to set this up as a stoichiometry table. We're going to get some moles of this. We're going to get some moles of this. If I remember correctly, this is going to be our limiting reactant. We're going to subtract. We're going to subtract. We're going to add. We're going to get moles that are made. Then we're going to do an ice table to see how much of that redissolves. When we've got some excess, if I remember correctly, it's 0.01149. You're going to have some excess, or 47. It's 0.0114 something. You're going to have some excess sodium iodate, and then you're just going to set up the equilibrium going backwards with the barium iodate. Now, if this is going too fast for you, don't worry. We're actually going to do it when we do problem 2. Was there a question in the hallway?
Yeah.
Okay. We're going to go ahead and do this. We're going to go to barium 2 plus 2 IO3 minus. We're going to have some 0.0114 there. We're going to have 0 there because we've essentially got in our reaction with the barium chloride being our limiting reactant, we've got 0. We're going to have plus x plus 2x. And in this case, we actually can use the x is small approximation.
Isn't the 0.0114 shouldn't be that's in moles?
No, you divide it by the total volume. Yeah.
Oh, right. I forgot to divide by 0.5.
The molarity is going to be 0.0228.
Thank you.
For the concentration of the...
Yeah. Now, that makes sense, right? Notice my concentration that I had in excess is barely different, which makes sense because I'm adding milligrams of material, right? I'm adding a small amount of material, so it makes sense that my initial my starting concentration and my initial concentration after the reaction are about the same. Then we solve the ice table, and that gets us how much barium there is, or how much barium redissolves, and you find that a very small amount redissolves.
So
now, yeah, go ahead, question. No, go. What were you going to say?
So
I was about to move on.
When it's asking if the amount redissolved is significant, how do we get the percentage?
So for determining whether the amount that redissolves is significant, you're going to compare. You're going to essentially turn this x into moles to get how many moles redissolved, and you're going to compare it to the moles here of how much solid you had, right? So if you had like 1 mole here and you had like 0.01 mole here, that would be 1% redissolved.
Yeah.
That's not what you get in this problem, but that's how you would do the comparison. Question there, then there.
Why are you dividing the 0.0114 by 0.5?
Because when we do, so this table down here is an ice table, and that's in moles, because I got sloppy with my units because I was going fast. This is in moles, and I need this so that it's in molarity. That 0.5 is 0.5 liters, because I need this in molarity.
Stoichiometry tables are always with moles, right?
Stoichiometry tables are always with moles. Equilibrium tables are always with molarity. Question here, then there.
Where's the cutoff point for significance? Is there like a specific, because like when it said like for moles.
10%. Remember, so we're using the same kind of like rule of thumb. It depends on how careful we want to be. For this class, I'm okay with like 10%. Oh, I shouldn't say that on film. Most classes are okay with 5%. Once you get into your higher chemistry classes, 1% error is too much. So, depending on how careful you want to be. If you're going into biomedical sciences, 1% error might kill somebody. Right? So, it depends on how... making solutions, it's okay. So, you have to consider what's significant in the context of the problem. And in these problems, I'm okay with 10%. Let's actually do number 2 now. Are we ready? Oh, another question. Oh, I jumped through the stoichiometry real quick. So this came from 0.5 liters times 0.023 molarity minus the moles of barium 2+. right? So I jumped through the stoichiometry. I did this problem like 3 times in the last, I don't know how long. So I jumped through it quite quickly. But we're actually going to slow down and do it step by step for problem 2 right now. So let's go ahead and look at problem 2 step by step and make sure that we can do it. So if I remember correctly, this is 0.22 molarity silver nitrate. And how many milliliters did we have? A couple more people can move in. A couple people have left if you want to get a little bit closer. And we're going to add that to, was it 40-something milliliters? 80-something milliliters? 83 milliliters of 0.22 molarity. Sodium, was it sulfate, SO4? The KSP, AgSO4.
What 1.2 times 10 to the -5?
Anyone else get that?
Yeah.
Cool, okay. So, essentially what we're doing here is we're going to look at this step by step, and if I remember correctly, step A says, or part A says,
How much silver sulfate forms during the reaction step in moles?
how much, so couple good hints in that problem, right? How much tells us stoichiometry. Forms tells us stoichiometry. In moles tells us stoichiometry, right? There are different words that give us different clues. We've got a lot of clues that tells us we're doing stoichiometry. So I'm going to look at AgNO3 aqueous plus, so we're looking at problem 2, part A, AgNO3 aqueous plus, that's not an A, there we go, Na2SO4 aqueous goes to Ag2SO4 solid plus sodium nitrate. I don't care about the sodium nitrate. It's uninteresting. I need to get my number of moles. We're gonna have 35 times 0.22. I'm just gonna do it in millimoles, which might drive you all crazy. But I get tired of dividing by 1,000 just so I can multiply by 1,000 later.
Once you balance it, I think there's a 2 in front of the AgNO3.
Oh my goodness, there is. I hopefully would have caught that when I went to the reaction part, but I don't need that for the initial moles. So this is 7.7 millimoles. And this is 83 times 0.22. (18.26 millimoles). Now, I look at this, and I'm just going to do some mental math. I say if I double it, I need twice as much. Based on the recipe, the chemical equation, I need twice as much silver as sodium sulfate, silver nitrate as sodium sulfate. If I doubled my silver nitrate, I would only have 15.4. That's not double, so I know my silver nitrate is going to be limiting. So I'm going to minus 7.7, minus 7.7, plus 7.7. Don't forget your mole ratios. 2 to 2, 1 to 2, and 1 to 2. Right? For every 2 moles of silver I have, or silver nitrate, I make 1 mole of silver sulfate. I then go ahead and get, if I did this right, my excess, my limiting reactant should go to 0. My excess reactant I can't divide that in my head for some reason. Like 3.5, 30, no. 18 minus 3, 15 something, 14 something?
14, 40, 41.
I have some millimoles left over. So that is my excess reactant. Notice I must have done the right thing because it's not a negative number. So that's a good thing. And then I can go ahead and say I started with 0 there. The amount of solid silver sulfate I make in moles is going to be, I can't divide that by 2 in my head. 3.85? If you don't like millimoles, you can just call this 3.85 times 10 to the minus 3 moles. Just like millimeters to meters. So that is how much we made. That is part A. Just doing the stoichiometry. You should all be stoichiometry pros at this point, yeah? Yeah. Okay. Part B.
So part B is what is the excess reactant in its concentration?
What is the excess reactant? Sodium sulfate is the excess reactant. What is the concentration? And notice this is setting us up for the second part that we want to do, the redissolve. Because when I do the ice table, I want this in concentration. So I'm going to say the concentration of sodium sulfate is going to be 14.41 divided by 83 plus 35. That's 113 milliliters. Is that right? Can I do math in my head? Oh, 118. Yep, I was off by 5. 118. I cannot do math in my head, it turns out. Then when we divide these two, notice since it's in millimoles and milliliters, the 10 to the minus 3 there, the 10 to the minus 3 there cancels. This is essentially moles per liter. That's why I like millimoles. I don't have to divide by 1,000 and multiply by 1,000. If you're hating millimoles, try it a little bit. It just is faster. It's faster. I can't do this division in my head either, but I think it's going to be about 0.12. 0.122 molarity. That is my sodium sulfate concentration. That's part B. That is setting us up. A, B. That is setting us up for, I think, part C. What's part C ask us to do?
What is the concentration of silver ions and sulfate ions at equilibrium?
So notice, we've done the stoichiometry like we're in Chem 127, and we're like, yay, the reaction goes to completion, and we make products. In 128, we say, no, boo, zeros are not energetically balanced. So some of this solid, again, we've overestimated how much solid we formed, and now some of this solid has to redissolve. So we're going to go ahead, and I need more space. I'm going to leave those things in boxes for a moment. And we are going to redissolve some of our solid. Part C, we have to say, okay, this was too much, right? We didn't take the energetics into account. We just pretended like the reaction went to completion. So if we're actually going to go ahead and do the redissolve, I'm going to look at silver sulfate and look at how much of that silver sulfate falls apart into 2 Ag plus SO4, 2 minus aqueous. Now, my sulfate concentration is going to be the same as my sodium sulfate concentration. Remember, the sodium is just a spectator ion. Doesn't really matter. So when I'm looking at my initial, because of step B, I'm not going to make the mistake I made last time and forget to divide. I'm going to put 122 units of molarity. I'm going to have 0 silver because technically I think I precipitated. Well, I said I precipitated all of it, but I know that some of it shouldn't be precipitated. Question?
How do you know which was spectator ion?
The 2 solubility rules I expect everybody to remember are that sodium compounds are always soluble and nitrate compounds are always soluble. So sodium ions and nitrate ions are always going to be soluble, except for in the sodium test, which is really weird and involves uranium. I think some of you are doing it this week. Or did some of you do it this morning? Or is that next week?
This morning.
This morning? Did you do the sodium test this morning?
I think so.
Yeah, that one's weird. There's only one compound that precipitates sodium and actually has uranium in it. Other than that one, though, sorry, it blows my mind just thinking about it. But other than that, sodium ions are always soluble. Nitrate ions are always soluble. So sodiums and nitrates are pretty much always spectator ions. They're never going to precipitate with anything. So I can set up my ice table. Now, we'll do it this way. We're going to have our plus 2x plus x. We're going to have 2x. Finally, we can use the x is small approximation again. 0.122 molarity. I'm then going to say KSP 1.2 times 10 to the minus 5 is equal to 2x squared times 0.122 molarity. Solve for x. I'm going to cheat a little bit. I'm going to call this 0.12 so I get really nice math. One times 10 to the minus 4. That's a 4 would be 0.25 times 10 to the minus 4. Square root of 25. Someone check me. 5 times 10 to the minus 2?
Minus 3.
Is it minus 3?
I got
5 times 10 to the minus 3 molarity. Whoa, wait, no, really? That's what you get for x?
Yeah, you'll get some of the negatives that are
Wow. That's funny. Why is that funny? What do you mean? No, this is something else curious. I'm checking some other math in my head now.
Oh.
You don't have to solve the quadratic. X's small approximation still works. 0.122 is still small, is still large compared to this. X's small approximation is fine. There's a problem someplace else that's really funny, like borderline hilarious. Not really. So, what's part D ask?
How much silver sulfate redissolves during the equilibrium step? And part C in moles.
So if I made this much silver sulfate and this much redissolves, what's the problem?
Oh, wait, no.
I'm dissolving more silver sulfate than I made.
Aren't those in different units?
Yeah.
Oh, they are, thank goodness. Oh, jeez, that was what's freaking me out. Okay, let's get this into moles so we can actually compare. Yeah, that's moles molarity. That was freaking me out. That's why I was like weirded out for the last like 2 minutes. Let's go ahead and take this molarity. We're going to multiply by 0.118 liters.
Wait, what do we multiply by 2 for
No, because we want it's 2 for the silver, but that is going to be 1 mole silver sulfate. Remember, the way we're setting this up is always so the axis in terms of the solid falling apart. So I'm going to multiply this by the 0.118 liters, and that will get me the number of moles that redissolve, and then I won't be freaking out as much.
If we're using millimoles and you ask for moles, do we need to convert it to
If I'm asking for moles, you can leave it in millimoles. I know what it means.
Okay.
This is going to be like 5 times 10 to the minus 4, but actually help me out. It's going to be like 5.2 times 10 to the minus 4, something like that. 5.9. Oh. Oh, that makes sense. 10 to the minus 4? And now we're in moles, and now we can compare. So, is the amount that redissolves significant? Yeah. If we looked at this, I could rewrite this as 0.59 times 10 to the minus 3, right? Just moving the decimal place over. And I do that so that these are comparable. I'm dissolving about 20% of my solid, right? 3.85 times 10 to the minus 3 minus 0.59 times 10 to the minus 3 is like 3.3. That's a pretty significant change in the amount of solid I formed. So in problem 1, you find that the amount that redissolves is not that significant. You get like a 0.1, you get like a 1% error. In this problem, problem 2, you actually find that the amount of solid that redissolves, the amount that we overestimated to precipitate, is almost 20% an overestimation. We overestimate by quite a bit in terms of how much solid precipitate forms. And so we do this calculation, and the reason that problem 2 has the extra step of what's your net amount, how much solid do you actually form, is because in this problem you actually have to subtract the amount that redissolves to get your net amount of solid formed, which I think is part D. Part D, you would just do 3.85 minus 0.59 all times 10 to the minus 3.
Where do you get those numbers from?
3.85 was from part A, and how much solid we originally formed. Or sorry, part B, because A was, no, from part A. 0.59 times 10 to the minus 3 was from part C, how much redissolved. And then I just subtract the two from each other, which I can almost do in my head. 3.27? 26. That's an S. That's the net amount in moles that we actually made. So in this case, our overestimation in the stoichiometry was actually significant. Question?
Sorry, so the 5.9 times 10 to the negative 3 is how much a silver dissolved?
Yeah, the silver sulfate precipitate that we formed. And I changed it so it's 0.59 times 10 to the minus 3 just so I could easily compare these numbers.
Do we have to multiply by 2 since it's 2x, or do we just leave it?
No, because remember, we're looking at how much of this redissolves. So every one of these that redissolves makes 2 of this. But we solved for x, so it's got the 1-to-2 ratio already in it.
Could you say that again? Sorry.
So the way we set up the problem, calling this 2x, already took into account the mole ratio. The way we set up the problem already took into account that mole ratio.
No question.
Yeah.
Why are you subtracting the amount that forms by the amount that redissolves within there?
So this is, again, we're recognizing the fact that when we do stoichiometry, we're not taking energetics into account, right? We're just saying it goes all the way. And what we're realizing is that saying it goes all the way is a mistake, and we need to take the energetics into account. And when we do, it's like, oh, actually we make less than we thought.
Okay.
In most of our calculations, the redissolve amount is negligible, and it doesn't matter. In problem 1, in the homework, and all the problems on homework 1, and the problem 1 and homework 2, the redissolve amount has always been insignificant. It's always been like 5 orders of magnitude, 3 orders of magnitude off, and it hasn't mattered. Problem 2 on homework 2 is the first time where it's like, wow, this is actually a significant amount of redissolve. Because we made such a small amount of solid and the equilibrium constant is actually not that small, that redissolve actually becomes significant. Cool. So that's problem 1, problem 2, and 3, and I'm not doing problem 4 because it's just the same as problem 3. I'd be repeating myself a whole bunch.
There's the last part that's asking for the percent error.
Oh, percent error, you would compare the 3.85 you originally predicted. So this would be like your theoretical, and then 3.26 would be your actual.
Okay.
So you do 3.85 minus 3.26 divided by 3.26. And you should get something that's approximately like 17 or 25% error, something in that range. Do you all remember how to do percent error? So depending on how you see percent error written, almost looks like a percent sign. You do this thing. Right, you do actual minus 3. I always throw an absolute value on there. Actual minus 3 divided by actual. The thing that becomes problematic is normally when we use this, the actual is what you're experimentally determining, like what you do in lab, and the theory is what you do on paper. It's a little more strange when you're doing paper calculations and comparing them. So the actual in this case would be your net amount, and your theory would be just the stoichiometric amount. And it's important to make that distinction. And you should get something that's like, I think, a 20%-ish error. I'm not doing that right now, but 20%-ish. I want to take a moment to open up to questions about the labs or questions about anything else as well. And have I been neglecting any 124 students? Has anyone from 124 just like walked by and like then been like, never mind? Hey, how's it going? Sorry about that.
I'm doing other work. It's okay.
Okay.
I can wait till you're done, and then like I'll just wait for a little bit more.
Sounds good. I'll be out there in just a moment.
I have a question.
Yeah.
What are the questions asked? Oh, never mind. I thought it was part 4. That's exciting. Never mind.
Oh, part you were looking at
F5.
problem
because
5.
I thought it was like a letter, but it's not a letter.
Oh, okay. Do we have any questions about the lab? I feel like we've covered everything we can in the homework right now. Lab questions? Yeah, question in the hallway. Yeah. Yeah. Let me see if there's any other questions. We did that earlier. I'll stop the video and we can repeat some problems. Okay, cool. I'll see you all for the quiz in a little bit.
So what's your plan to be?
They're not.